by Karmen Grizelj on Harish-Chandra maps and primitive invariants. So take it away.
So, hello everyone and welcome. So I will be talking about Harish-Chandra map and what it, let's say, does to the primitive invariants. Before we start, I would like to thank the Center of Excellence, Quantix for supporting this research, and also to the people at the seminar for having me here. So we start with a complex semi-simple Lie algebra. That's something that has been done like a few decades ago. So that's a bit old, but it will give us motivation to do what we are doing. So in case you are not comfortable with Lie algebras, you can just take any associative algebra and just define a Lie bracket like a usual commutator, and it will have all the properties that are required. In fact, this is something we mostly do because most of the time we can just behave that we're talking about matrices. So you know how to make a commutator of matrices, and that will be our Lie bracket. Now, once you have a Lie bracket, using it, you can define something called the adjoint representation. So you just send any element X to a mapping, which is just applying Lie bracket on elements. Now, I guess I erased that one, but also what I'm going to need is symmetric bilinear form. So B will stand for symmetric bilinear form, which can be defined in such a way. It's also called the killing form. And you can say that G is semi-simple if B is non-degenerate on G. So for now, we'll be working with this kind of algebra. Now, what I'm going to need are three algebras. Well, I wrote the definition for these definitions, the first two, or any vector space, although we will be mostly using Lie algebras. So the exterior algebra, I guess you are familiar with that one. So it's just algebra generated by the space V and is given by relations x times x equals 0, or you can say that elements of degree 1 anti-commute. The Clifford algebra is somewhat similar. So to define a Clifford algebra, you not only need a vector space, you also need a bilinear form, which I already defined. So again, you will have the algebra generated by V, but this time with relations that x times x is minus bxx. Note that if we set B to be trivial, then Clifford algebra is actually exterior algebra at the same time. And actually, whichever bilinear form we choose, we get the same dimension. That would be 2 to the power of dimension of V. But these two guys are not isomorphic unless B is equal to 0. And the only infinite dimensional algebra I'll be needing is the universal enveloping algebra. So as I said over there, any associative algebra is automatically a Lie algebra with the Lie bracket defined in that way. But not every Lie algebra is an associative algebra. So if you want to go from a Lie algebra to an associative algebra, unfortunately, your construction is infinitely dimensional. So we get our Lie algebra, generate a tensor algebra with the elements of G, and put these relations that just say that Lie bracket is a commutator. But this one is always infinitely dimensional. Now, inside of those, we will need some special spaces. The first one will be the space of invariants. So I wrote the definition here. It's just all the elements of the exterior algebra. So I will be calling them exterior invariants or skew symmetric invariants. So those are all the elements of this exterior algebra that are annihilated by all the adjoint actions. When speaking of the invariants, one thing is clear, that constants, which would be degree 0 in this guy, all of the constants are definitely invariant. And also, if you have an invariant and you add a constant to it, the invariance doesn't change. So we try to make our job a bit simpler by just removing those constants. Why are we removing them? I'm not sure I will have enough time to explain it. It's actually important for some proofs. So what you do is just consider elements in here that don't have a constant term. And in general, something like that would be called the augmentation ideal. Or maybe you've seen the augmentation map, which just gives you the constant term. So this would be just the kernel of the augmentation map. So now that we have that, and we have that bilinear form, it was originally on G, but it can be extended complement with respect to B, or the square of this augmentation idea. Now, there are some results about these primitive invariants. First of all, the dimension of that space is the rank of G. And the inclusion of the primitive invariants to all the invariants extends to an isomorphism from exterior algebra of P to J. So with respect to the bilinear form B. So that's why I was saying originally we had B on just the Lie algebra, but it can be extended to the whole exterior algebra by using determinant in the same degree, and all different degrees are automatically orthogonal. So that's how you define the bilinear form. Yes. Yes, 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 yes. No, no worries. Well, if you take add x on then it's just y like this, and so on for the higher powers. Sorry? Okay. So the first quite old result, this Hopf-Kožul-Samuelson theorem, actually states that the invariants are the exterior algebra of primitive invariants. And Constant went a step further and actually concluded that the invariants have a structure of a Clifford algebra of primitive invariants. Remember, those two, exterior and Clifford algebra, are not isomorphic. So you have to do a few adjustments here. First of all, this Q, that would be this, what's it called? Either Chevalier map or quantization map. So should I define it, or that's a bijection, actually vector space isomorphism from the exterior algebra to the Clifford algebra doing this. So of course, constants are untouched, but you have to take an orthonormal basis. So in terms of the orthonormal basis Z, it just moves the exterior or wedge product to the Clifford product. Yeah, actually, I'm constantly saying that these two are not isomorphic, but yeah, I never said why, and it's actually super easy to conclude. Well, the exterior algebra is graded, the Clifford algebra is not. So first we need to take our invariants and make them Clifford invariants. And then we take a Clifford algebra of P, but not with the same bilinear form anymore. We have to take this B0, but it just changes some signs in some degrees. So I'm not going to write that down. It's simply a technical detail. So it also has a Clifford algebra structure. And now this mapping alpha, which is like the only complicated mapping I'll be using, is mapping defined in this way. On G, you define it with this formula. So you take BI to be dual basis of G, make the commutators, this is Clifford product. And that's what you do for X in G. And then using the universal property of the universal enveloping algebra, you extend it to the whole universal enveloping algebra. And if we denote by E the image of that whole mapping, then Constant proved that the Clifford algebra of G is a tensor product of that image of alpha and the invariants. And remember, invariants were a Clifford algebra of primitive invariants. Now, this part I had to write it down because otherwise I'm not allowed to call anything row decomposition. So a row would be just, which is kind of standard in representation theory, half of the sum of the positive roots once you fix positive roots. And V row mapping called contraction. So again, you define it on G and extend it to the exterior algebra. Another way to define a contraction would be to say that it's any derivation of degree -1. So this is called contraction. I guess it's kind of expected that the degree is exactly -1. Does somebody have a question? Oh, okay. Okay, you feel free to. So now there is this statement which doesn't look very cool. Is by now the only thing that's left. So if I get some time, I might discuss the idea of the proof. The thing is, we have to introduce some more algebras in order to work with this, namely the symmetric algebra and the Weil algebra. And yeah, both of them are also infinite dimensional, but it turns out that it's easier to work on them than on this exterior algebra. So, okay, this statement on its own doesn't mean much. Okay, you contract a primitive invariant, you end up in the image of alpha. Wow, big deal. But there are many things you can do with just that statement. First of them is actually what was kind of the goal of whole Constant's research. What does this equation actually mean? Remember the theorem that the Clifford algebra is the tensor product of E and J. Okay, good, but we don't know how this E and J kind of sit in this decomposition. We get an element of a Clifford algebra, but we don't know how to express it in terms of this tensor product. Unfortunately, that still remains as it is. We can't express any element of a Clifford algebra like that, but we at least got it for the basic space G. So from the previous theorem, this first part is in E, and the second part is in J because it's invariant. If it's primitive invariant, then it's also a normal invariant. So Pi and Qi are just the basis for primitive elements. Okay, that's some nice result to say like, okay, now we can see what something looks like. But we can go a bit further and introduce Harish-Chandra map. So you might have heard of Harish-Chandra map, but it looked a bit different than this. This is like a Clifford version of it. So what we do is take the triangular decomposition. So n plus corresponds to positive roots, or those are positive root vectors. These are n minus would be negative root vectors, and age would be Cartan subalgebra. So then, using Poincare-Birkhoff-Witt basis, we can make a decomposition like this. And then we can just project from the whole Clifford algebra to the Clifford algebra of H. And with respect to this decomposition, of course. Such a map will be called Harish-Chandra map. Unfortunately, this map is not a homomorphism. But if we decide to restrict it a bit, if we decide to consider only some invariants, we get not only homomorphism, we get an algebra isomorphism, as the next theorem states. So once we restrict the domain to age invariants, we get an isomorphism. Not just that, but in these invariants, there are also primitive invariants. And if we look what happens to the primitive invariants when mu applied, it actually has to end up in the first degree of the Clifford algebra. Well, first degree, I mean filtration degree. As I said, it's not graded, so we can only talk about filtration degree. So yeah, that's another result from Baslov, that we actually get a vector space isomorphism between P and H using Harish-Chandra map. Yes. Yuri, yes. Yes. This is a bit the old parts were Kožul-Samuelson and constant, and now this part is kind of, yeah, Baslov was using Constant's results I mentioned. In fact, to prove this last theorem, he had to use that theorem that I said doesn't look like very much on its own, but it's actually a crucial statement in proving this last theorem. So yeah, these things, well, okay, I put it into history just because it's like this semi-simple complex part, and like present and future will be reductive case. So yeah, this is more recent. And finally, the things we are trying to do. So inspired by the case of semi-simple complex algebras, we move our attention to reductively algebras. Now, what is a reductively algebra? Well, it's just a semi-simple algebra plus something abelian. So it is a larger class than semi-simple, but like not very much. And now we take the Cartan decomposition, but we don't take just any. So now maybe some of you might remember my talk from the summer about taking Cartan subalgebra, and back then I said that there can be many Cartan subalgebras. They'll have the same dimension and like everything is nice. That's why we can actually define a rank. But in this construction we are doing, we are actually choosing a subalgebra, a Cartan subalgebra that is unique. So this one is called a fundamental Cartan. So what we are actually doing here, as before, you can take like any maximal abelian subalgebra, but if you want to kind of separate this age into two parts evenly in a way, then you do something like this. You take so-called Cartan involution. I'm not going to define it in general. I will just say that when we are working with matrices, it's just minus X transpose. And now I guess you can all tell me what could be the eigenvalues of an involution. No, I'm asking about eigenvalues. Plus minus 1. And then you say that K is the eigenspace for plus 1, P is the eigenspace for minus 1. In other words, these will be anti-symmetric matrices, as you said, and these will be symmetric matrices. And now, how do we choose this age? Well, we choose this age so that it kind of respects this so-called Cartan decomposition. We do it in a way that if we denote by T, this plus 1 part in age, then this guy has to be a Cartan subalgebra of K. So K is Lie algebra itself, P is not. Well, if you make a commutator of two guys in P, you end up in K, so it's not a Lie algebra. And the Cartan subalgebra is unique if we require something like that. So that's how we choose our Cartan Sabel. I guess so. So as it was the case with constant, it is nice to know that the Clifford algebra of P, remember Clifford algebra just required a vector space, not an algebra. So we can actually have a Clifford algebra of P. It also admits the row decomposition. Now, so this small guy here is K. So K invariants in the Clifford algebra of P. The only thing is now alpha, well, it has the same formula, but it's not the same mapping for sure. Now our, oops, what have I done? Here, okay. Alpha now goes from universal algebra of K to the Clifford algebra of P, and on K, it is defined by that same formula, minus 1/4 sum of X commutator BI DI, but this time BI and DI are dual bases of P. And when commuting something from K and something from P, we end up in P. So it's fine. This really is a product of two elements of P. So it is inside of the Clifford algebra of P. And again, extended to the whole universal enveloping algebra. So we have that nice decomposition. And again, I want to define a Harish-Chandra map in this so-called relative case. Well, yes, maybe I should be mentioning that a bit later, but I guess I can make a 1 minute break to say what is a bit of a problem when working with this relative case. Before, you had something like, here was G, here was G, this was basis of G, these were elements of G, and now we end up with this decomposition. And anywhere you see G in previous constructions, proofs, theorems, whatever, you just had G. Now, that G has to be replaced either by K or P, and sometimes it actually stays G. And now imagine if you just want to combine like 3 things, it's already 27 possibilities to combine the letters. Okay, well, of course, for some of them, we immediately know it's not the right way of doing things, but yeah, it's a kind of, it's a bit of a problem to actually know for sure if it's better to define something on a smaller space or a bigger space, or maybe this orthogonal space. So yeah, that's, I would say we are playing some combinatorics, but no, actually it's more try and guess. But okay, I hope we finally managed to kind of agree on which spaces should be used where. So as before, now we can Also, write P as a direct sum of its abelian part. Abelian part is denoted by A. Its positive part and negative part, meaning positive root vectors and negative root vectors inside of P. And now that we have this decomposition on the Clifford algebra, we define the Harish-Chandra map in the same way. And again, this map is not a homomorphism, but I'm proud to say that I managed to prove that if we restrict to K invariants, we actually get an algebra isomorphism. In the case of G being SLO. So G is SL 1 plus 1 R. And then K would be just SO. Now, of course, someone mean could say, oh, big deal, you proved it not even for all the special linear algebras, just for half of them. Okay, that is true. But these guys and another exceptional Lie algebra, I'm not going to guess which one it is because I'm going to tell it wrong for sure, are the only ones with the property that the GH roots are the same as GT roots. So in order to define roots, you need something abelian. And what is usually done is you just take maximal abelian subalgebra. But this P, okay, it is a Cartan subalgebra for K, but it's also some abelian subalgebra inside of G, which means you can also look at the T roots. And of course, generally speaking, these two are not the same. But if we assume that nothing changes by restricting our abelian part a bit, then the only options you have are these and that exceptional one, maybe G2. Even for SL even, that's not going to be true anymore. So that's the first result. And as I mentioned, the hardest part is to prove that contractions end up in the image of alpha, which we are working on. But once we manage to prove that, and I am quite positive we will, because in small examples, it turned out to be true. Then I know a proof that a corollary of this one is the same thing Baslog had, that the Harish-Chandra map is actually a bijection between primitive invariants and A being the abelian part of P. So yeah, now this P, and once I can remove this T and write theorem, I'm going to get my PhD, I think. So, okay, well, that was actually a nice time management. Good job, Grizelj. Thank you very much. I guess we have a few minutes for questions.
Do we have any questions? And can those question askers try to use the microphone?
Could you explain a bit again the automorphism and how you're defining this? I don't think I got it all. How you this Cartan decomposition?
Yes. I guess it will be better if I write it here. Well, in general, a Cartan decomposition is Cartan involution is an involution that somewhat behaves nicely with respect to the bilinear form. But okay, is it fine if I just stick to this Cartan involution? So we have a Cartan involution which has eigenvalues plus minus 1. Not just that, but the whole space actually can be decomposed into these two eigenspaces. And then we call no. In this case, this was my definition of the Cartan involution. So minus transpose, that's the most common one when working with matrices, which I am doing. But as I said, in general, I say that there is this just one equality that has to be satisfied for an involution to be called a Cartan involution. Yes, and not only you get direct sum, you actually get an orthogonal sum. So K and P are actually orthogonal. K was SO, or if you wish, anti-symmetric matrices, and P was symmetric matrices. Of course, by choosing another Cartan involution, you would get another K and P, but these guys seem to be quite nice to work with, so sure, why not? I was just about to say, yeah, I was like, wait, I wanted to say something to Re, and then I forgot. On a Lie group level, you would get something like this, and K would actually be a maximal compact subgroup. If it helps. And of course, this would be Lie algebra of this group and so on. So if you want to think on the level of Lie groups, yes, again, Cartan involution. And well, if you remember that the construction going from a group to the algebra, the same thing also happens with the Cartan involution. If you have it on groups, you kind of differentiate it and get that guy. So I guess it might be something like this, or yeah, that might be the Cartan involution for groups. But you know me, I stay away from groups as long as I can. So if I missed something here, I hope you will excuse me, because yeah, I would have to go back. So yeah.
Any other questions? If not, let's thank Karmen again. And we're going to take a 10-minute break before Elmarie gives his talk.